This is the second and final SLO6 video. Today we'll be covering section 6.2, the binomial distribution, in chapter 6, which is all about discrete random variables and probability distributions, right? Now, last time we learned about discrete random variables in general. We're going to look at one in particular that behaves pretty nicely, the binomial distribution. A binomial distribution, also I've seen it called a binomial experiment, is an experiment in which the following 5 things occur. There is a fixed number of trials, which we denote with n. All trials are independent. Remember that word from last time? It means they don't depend on each other. They don't affect each other, right? And under identical circumstances. Now, this book doesn't mention the second part, but what it really means is that basically each trial is exactly the same as all the others. Another one. Each trial has exactly 2 outcomes, success and failure. Now, it's worth pointing out that success isn't necessarily a good thing. It just means the thing we're interested in. And then all trials have the same probability of success and failure, where the probability of success is, we denote it as lowercase p, and so the probability of failure is 1 minus p, right? Remember complements, right? The random variable, big X, represents the number of successes out of n. Sorry, that should have been out of n trials. Okay. Now, let's just consider the following examples from the textbook. I just ripped this right from the reading, which I hope you're doing. Now, it says, determine whether each of the following are binomial random variables, right? And if it is a binomial, then, find its stuff, right? So let's see, a fair coin is tossed 10 times. X is the number of times the coin lands heads or tails. Now, we know, okay, n is going to equal 10, right? It's a fixed number of trials, so that's a good sign. X is the number of times a coin lands heads. That's a good sign because we know that a coin can land only head or tails. So that works. So let me just write here, outcomes H or T. That also works. They say also state the values of n and p. We should know that the probability of heads, a success, is going to equal 0.5. Which it turns out is the probability of the failure too, right? Just in this case. We also know that all coin flips are going to be independent and identical, right? The probabilities are all going to be the same. So, yes. Give it the green check mark. Yes. This is a binomial distribution. This X is a binomial. So, X is a binomial random variable. Okay? So, that's good. Let's look at part B. Looks innocent enough. 5 basketball players each attempt a free throw. Let X be the number of free throws made. Let's pause that one, see if you can get that. Are you thinking it's yes? Turns out the answer is no. Maybe pause it for another 10 seconds. Think about why. The reason is because 5 basketball players, all of whom might have very different skill levels, are attempting a free throw. So, each attempt may be independent, but they're not identical, is not identical as the players have different free throw percentages. So, probability of success is not constant, right? It's not a single value. Now, how could we have made it a binomial random variable? If we had instead changed this to 1 player attempts 5 free throws. That's a binomial random variable, right? Because that's an example of 1 player with the same skill level trying something 5 times. The probability of each trial is going to be the same. All right? So that's that one. And then part C, let's see. 10 cards in the box, 5 red, 5 green. Cards are drawn without replacements. X is the number of red cards drawn. Now this might look okay, except if we had made it, if it were this, then it would have been binomial. But because it's without, it's just not, right? 3 cards are drawn. So, probability of getting a red card drawn is going to equal 5 out of 10 at first. If a red is drawn, then the probability of red drops down to 4 out of 9, right? Because there are 9 cards remaining and only 4 are red, which is not the same as 5 out of 10. And if a red is not drawn, then the probability of a success is 5 out of 9, which is also not the same as 5/10. So P, the probability of, let me just actually write it like this, the probability of a success, again, isn't constant. So, no to these guys, right? Again, if we had done this, we would have been okay, but we didn't, okay? Now, there is an exception to this rule. There is an exception. If the probability of success is, let's say there are a whole bunch of trials, and the probability of success is changed by a very, very, very small amount, then we can still model it using a binomial distribution. I'll discuss this more in class. There's an example in the in-class question sheet that deals with this. But we're going to move on. So we can use Minitab to determine the probability of getting R successes in N's trials. That's the main question. With a binomial distribution. But we're going to derive the formula first. You never have to use it, but we're still going to derive it. It's not so bad. So suppose we've got a fair 6-sided die, right? The probability of each rolling each number is 1 out of 6. We're going to roll it 4 times. We're going to be interested in the number of ones rolled, okay? Or the probability that, a certain number of ones are rolled, right? What's the probability that 0 ones are rolled? Well, that's not that hard, right? Probability of 0, maybe I'll write it like this, 0 ones. Well, that's going to equal, well, let's see, what's the probability of rolling not a 1? It's going to be 5 out of 6. Well, each die roll is independent and identical, so we get to multiply the probabilities, right? We just get to do this 4 times, right? Right, and it winds up being 5 to the 4th over 6 to the 4th, right? So let's see, I'm just going to enter that in the calculator really quickly. And I'm going to get this on my phone so you can't see it, but it's going to be 5 to the 4th divided by 6 to the 4th, and it equals about 0.48, okay? Now, the probability of getting 1 equals, well, let's think. We could get a 1 on the first roll, the second roll, the third roll, and the fourth roll. But then all the others have to be not 1, right? So suppose it's on the first roll. There's a 1 out of 6 chance of that happening. Then I guess the second, third, and fourth rolls, we did not get a 1, right? That's the probability of getting a 1 on the first roll. But we could have gotten it on the second roll, or the third roll, or the fourth roll, right? So what we're going to do is we're just going to multiply this. Let me actually scoot this equal sign over. We're going to multiply it by 4, right? Because this 1 out of 6 could have been here, or there, or there, or there, right? So it winds up being 4 times all that, and that winds up being, I'll do this on a calculator. Let's see, we're going to get 4 times, I guess that's going to be 5 to the 3rd, divided by 6 to the 4th. And that winds up being about 0.39. Okay. Probability of 2 ones. So, well, let's think about this. You could have a 1 rolled on the first 2, right? A 1, 1, and then not. you could have it done a 1, no, a 1, no. You could have it on the first and the fourth. You could have it on the second and the fourth. You could have it on the, oh, sorry, actually I missed one here. The second, I mean, probably best to do it this way. Second, third, second, fourth, and third and fourth, right? That's 6 different ways you could roll 1, right? So we're going to multiply by 6. 1, 6. 1, 6 times 1, 6. Those are the 2 times you can roll 1. Times 5, 6 times 5, 6. Those are the 2 times you don't roll 1, right? So this winds up being, just do it out, 25 over 6 cubed. Let's see what we get here. Excuse me. This winds up equaling about 0.12. There you go. By the way, these probabilities might have to a little bit higher than 1 just because of rounding errors. All right, so anyway, the probability of rolling 3 ones. Well, let's think about this. We could roll it on the first, second, and third, first, second, and fourth, first, third, and fourth, or second, third, and fourth. Right? In other words, there's one time where we're not rolling a 1. So again, we're multiplying by 4. All right, now let's see what we get here. That's going to be 20 divided by 6 to the 4th. And that is lovely. That is 0.02, I guess. 0.015. I'll say 0.02, okay? And then last but not least, probability of rolling 4 ones. And this is not that bad because this is just going to be 1/6 times 1, right? The only way for this to happen is you just roll 1 4 times in a row, right? So what's that going to be? Oh, that's 0.00, really. I mean, it's 0.0008, but that just rounds to 0.00, okay? So that's how you do it. And so the pattern here, this is just one example, but there is a pattern here. All right, and we're just going to generalize this to a formula. If you don't totally understand the formula, then that's okay. Just use Minitab or a calculator. But I want you to try to follow this, right? The notation Bn, P denotes the binomial distribution with n trials and probability P of a success, right? Probability of getting R successes in binomial experiment with n trials, and I should also say with probability of a success, equaling little p is, all right, this probability of R successes, actually maybe write it a little. In n trials is going to equal, now this is going to be n choose R times p to the r 1 minus p to the n minus r. And that winds up being, if you're interested, n factorial over r factorial times n minus r factorial. That's a minus sign. Times p to the r, 1 minus p to the n minus r. If this is a bunch of gibberish to you, then don't worry about it. I just wanted to write the formula down. If this does mean something to you, then awesome. Feel free to use it. Anyway, let us use this formula to find the probability of getting exactly 3 successes, at most 3 successes, and at least 3 successes for this situation, right? Where there are 10 trials and probability of a success is 0.4. Oh, I don't know why I made this all red. Let me make this all blue. Whatever. Oops. I don't know how I switched colors and didn't realize it, but whatever. Well, let's make that blue as well. All right, anyway. As we were, so the probability of 3 successes is going to equal, well, we're just going to use the formula. It's going to be 10 choose 3 times 0.4 to the third times 1 minus 0.4 to the 10 minus 3, or to the 7. Now, Google is actually a very nice calculator. I'm not really a big fan of you using Google during an assessment, but during class, you totally can, right? So let's see what we've got here. If we just do parentheses 10, choose 3, you can actually do that, and it'll actually know what you mean by that. Times 0.4 to the third times 1 minus 0.4 to the 7th. Make sure to use parentheses appropriately, right? 0.21, right? So that's what we're getting here. It's approximately, okay? It's a probability of exactly 3 successes. Probability of at most 3 successes. Well, how are we going to do that? Well, first we need to know, let me shove Google aside for a sec. Probability of at most 3 successes, since 0, 1, 2, and 3 successes are, remember the term, mutually exclusive, this equals the probability of 0 successes plus the probability of 1 success plus the probability of 2 successes plus the probability of 3 successes, which we know equals 0.21. So let's see what we wind up getting. Okay, so the probability of 0 successes, let's get the calculator back in here. So instead of 10 choose 3, we're just going to change our numbers, right? We're going to have 10 choose 0, which I'll tell you is just 1. 4 to the 0, 1 minus 0.4 to the 10. And that gives us 0.0, just rounded to 0.01. Yep. There we go. And we're just going to change our little formula right here. Again, the 0 becomes a 1. Enter it in, and so we get 0.04. All right, and then we change our formula again. And then this becomes to the 8th. To the 2. To the 2. And then 0.12. All right, so we add all these up. And again, we didn't need to do probability of 3. We already found that. That winds up being 0.33, 0.38. Okay, the probability of getting at most 3 successes. Remember, don't forget 0 in there, right? Don't forget that 0.01 in there, right? And then last but not least, the probability of getting at least 3 successes. That means I'd have to find the probability of 3, 4, 5, 6, 7, 8, 9, and 10. Annoying. I'd rather not. But there might be a shortcut. This is equal to 1 minus the probability of at most 2 successes. And we know what that is. It's just that, right? Let me highlight that so you can see. Right? So that's 1 minus 0.17, which is 0.83. Well, that saved us a bit of time. Okay. All right, next. Recall the expected value of a random variable. Remember, that's going to be If you want to write it all fancy, it's like that. But in practice, it's x1 times the probability of x1 plus blah, 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 plus xn times the probability of xn, right? And then the standard deviation, right? And by the way, we can call this the expected value of x equals. Standard deviation winds up being, right, we actually call this mu of x equals that. Sorry, actually, I shouldn't call it ex. I never use that term. We denote it as mu x, right? So this winds up being mu of x squared minus mu of x squared. That's the way it works, right? Anyway, it turns out the expected value of binomial distribution of NP winds up being very, very nice formula. That. The variance is this. Oh, sorry, that's the variance. And then the standard deviation is just the square root of that. Not quite as nice because of that ugly radical, but it's got to be there. All right. So anyway, last but not least, sometimes a problem just is too long to do by hand. Let's use Minitab to calculate the probability of at least 6 successes in a probability, or sorry, in a binomial experiment, blah. All right. So let's get open Minitab. All right. Calc. Probability distributions. Cumulative. Oh, that was interesting. That was unexpected. Let's see what it's doing there. That was not what we wanted. Okay, let's get. Okay, that's weird. We're just gonna do another blank project. Oh, there we go. Sorry about that. Calc. Probability distributions. Cumulative distribution function. Form of input, leave that the same. Distribution. Go to binomial. Number of trials was 15. Event probability was 0.3, right? In case you forgot. 15 and 0.3. Now, we want at least 6 successes. So, here's the thing. At least 6 successes, that's not exactly what we want, right? Because this is going to give us at most, okay? So what we're going to do, we're going to be a little clever. We're going to put in 5. Now watch what happens. The probability that we have at most 5 successes is 0.72. Now let's crop this guy. All right, and now let's just paste it in here. All right, so we have this. So the probability of at least 5 successes equals 0.72. So the probability, let's remember our basic complements, right? Yeah. The probability of at least 6 successes equals, let me make that a little nicer here, equals 1 minus 0.72, which is 0.28. Okay, and that's all we've got.